let's observe this problem here. We want to find the slope of the tangent line to the circle x squared plus y squared equals 1 at some generic point a comma b on the circle. So basically what I want to come up with here is sort of a formula for the slope of the tangent line for any point on the circle here. Right? So how do we go about this? Well, if we know what the point is, we could take the equation of the circle here, and we can try and solve for y. So we get y squared as 1 minus x squared. But the problem with this is we have to square root both sides, and then we get this plus minus here. Now, this is fine if we know that y is negative, then we use the negative square root. If we know y is positive, we use the positive square root. But that's a bunch of extra work, as it'll turn out, because we have to know ahead of time what the y value is. In this question, I'm asking you about just any old point on the circle, and I'm not telling you what it is. So, is there a way we can kind of answer this all at once? And it turns out there is. So, this, while it works, is inconvenient, let's say. Right, this doesn't really work for us. We'd have to split it into two cases and all that. So what's another way we can do this? Well, let's start with this equation here. Right? And what we're going to do is say, in this equation, y is implicitly defined as a function of x. Okay? So in this equation, y is implicitly defined as a function of x. So we kind of have y equals f of x. Okay? Now again, if we tried to explicitly solve for y, we would run into this trouble of, well, which value do we pick here? Do we pick the positive or the negative one? So we kind of are sort of picking the one that makes sense for that particular piece. But the reason we can do this is this allows us to do some tricks with the derivative here. Actually, I'm going to move this over. Oops. I'm going to move this over a little bit. Here. All right, so what we can do then is the exact same kind of trick we use to differentiate the logarithm. All right, so we're going to take the derivative of both sides of this equation. All right, so let's talk about what that derivative would be. All right, so here we differentiate x squared and we get 2x. What about the y squared? Well, again, that y squared is like f of x, so when we're computing the derivative of y squared, think of this as doing the derivative of f of x quantity squared. And now it's just a chain rule problem, right? The 2 comes out front, and we get our f of x left. So that's the derivative of the outside part, the x squared. Now we multiply by the derivative of the inside part, which is f prime of x. And if we swap these back for y's, this will be 2y dy dx. And so that's what goes up here. 2y dy dx. Because y is a function of x here. Right? And then here, derivative of 1 is just 0. Right? It's a derivative of a constant. So if we solve for dy dx, if we solve this, we wind up with minus x over y. Right? So what this allows us to do then is say, well, kind of as long as y is not 0, we can plug in the x value and the y value, and that gives us the slope. Okay? Now, it's even kind of interesting because if you think about a circle, when y equals 0, you're on kind of the left or the right edge. Right? And if you think about it, the tangent line is vertical there. In fact, let's draw a little sketch. Right? We have a sketch. Right? When y is 0 is when we would have these two tangent lines. But a vertical line has sort of an infinite slope, an undefined slope. And if we compare that to here, well, if y is 0, this is undefined. So it kind of makes sense. All right. So let's finish off the problem then. All right. So the slope at the point A comma B is m equals, it's just plug A comma B into this. So minus A over B. Right? And the tangent line, that shouldn't be capital, right? And the tangent line right? So here's the slope. So we'll do y minus b equals negative a over b, x minus a. Right? So here we kind of, we just did this very generically here, but we can, without actually solving for y, we can find these derivatives. All right? So hopefully that makes sense. Let's do this in one more example here. All right, let's compute dy dx, where y is implicitly defined as a function of x by the equation, let's see here, what should we pick? Let's do x squared minus 2xy plus y cubed equals 7. Right? So while it might be possible to solve for y here, it would be a lot harder than, say, in that equation for a circle. Right? So to do this, we're just going to differentiate both sides with respect to x. Right? So d dx of x squared minus 2xy plus y cubed equals d dx of 7. Right? So we're going to differentiate this. So the derivative of x squared is 2x. Now here, how do you think we differentiate this? How do you think we differentiate that? Well, the way to differentiate this is there's sort of two pieces to this, right? Right? Since there's two pieces, we just do the product rule. So minus, Right, so the derivative of the first is 2 times the second is y. And then plus the first times the derivative of the second. Derivative of y with respect to x is just dy dx. Okay? And then the y cubed, well, we did something similar to that before. It's just a chain rule problem. Right? So we'd get 3y squared times dy dx. Right? Over here, the derivative of 7 is just 0. Right? So what we need to do now is solve for dy dx. When we're doing this, what we're typically going to do is, well, we'll want to expand everything out here. So just to make sure we're all in shape for this. Right, so once we get everything expanded out the way it needs to be, what we want to do is gather all the terms with the derivative on one side and all the terms without a derivative on the other side. So in this case, it means we want to take these two and move them over there. Right? And additionally here, with the terms that are left over, we can factor out dy dx. So actually, let's do that in the next step. So here we have minus 2x dy dx plus 3y squared dy dx equals, when we subtract this over, minus 2x plus 2y. Right? Now we'll factor out our dy dx. So minus 2x plus 3y squared minus 2x plus 2y. And what's left to do? Well, we just divide by the stuff that's still there. So dy dx is minus 2x plus 2y over minus 2x plus 3y squared. And there we have it. That is the derivative of this, defined implicitly. Right, so it's pretty interesting here. So, you know, it avoids us having to explicitly solve for y to do a derivative. All right, so hopefully that makes sense, and we'll see you for the next one.